Hi my dear students, now we are going to discuss about variation of Z. Z means what? Z is nothing but it is the impedance. We learned this in the last class. Impedance is nothing but it is the net effective opposition offered by the combination of resistor of resistance R, inductor of inductance L and capacitor of capacitance C. When all these three elements are connected in an AC circuit, an AC current will pass through it. These three elements combinedly opposes the alternating current. That opposition is called as impedance. It is represented by the letter Z. How this impedance varies? Now let us discuss. Z is the impedance. The expression for Z is equal to root of R square plus XL minus XC the whole square. Yes, this is the expression for impedance which we learned in the last class. Z can be also found by using EMF and the current. So E0 by I0. Yes, these are the two expressions which are used to find the value of impedance. Z is equal to E0 by I0, Z equal to root of R square plus XL minus XC the whole square. Okay. Now we will discuss first thing when the impedance is minimum. When the impedance is minimum, we want to minimize the impedance. How? From this expression I can start. Z is equal to root of R square plus XL minus XC the whole square. Okay. This is R for resistance. We can't change the resistance in the circuit. It should be fixed. But XL and XC, we can change the value of XL and XC because XL is equal to L omega. XL is equal to L omega. Here L is fixed for a particular inductor, but omega is nothing but which is angular frequency. Omega is the angular frequency which we can change. Likewise, in the case of capacitive reactance, XC is equal to 1 by C omega. Here C is constant. In this case C is constant for a particular capacitor, but omega is angular frequency which is able to change. So we can change the angular frequency. If we can change the angular frequency, then the capacitive reactance as well as inductive reactance can able to change. So these two are variables. We can change this in terms of angular frequency, but the resistance cannot be changed. It is fixed. Okay. When the impedance is minimum, that is the first discussion going on. Okay, when the impedance is minimum, if the impedance is minimum, we want to minimize the impedance, then this term to be 0. XL minus XC is equal to 0. Consider if XL minus XC is equal to 0, that means the inductive reactance and the capacitive reactance is 0, then Z is equal to if XL equal to XC, sorry, XL minus XC equal to 0. If XL minus XC is equal to 0, then Z is equal to root of R square. That means Z is equal to R. That means the impedance is minimum. In this case, here the impedance is minimum, that will be equal to only the resistance, because XL and XC are cancel out each other, because XL minus XC is equal to 0. Then the impedance becomes resistance. That means impedance is minimized. Here in this case, only the resistor will oppose the flow of current. The capacitor and the inductor does not, because they cancel out each other. Okay, this is the condition for impedance becomes minimum. Okay. If XL minus XC is equal to 0, then XL is equal to L omega minus 1 by omega C is equal to 0. That means L omega is equal to 1 by omega C. when these omega come this side and L goes that side, omega into omega equal to omega square is equal to 1 by LC, or we can write omega is equal to 1 by root of LC. This is one of the important expression. Why sir? Why sir? What we have done here, XL minus XC is equal to 0, XL equal to L omega, XC equal to 1 by omega C. Then L omega equal to, this go to that side, that will become positive 1 by omega C. Omega into omega, omega square is equal to L, omega square is equal to 1 by LC, or omega is equal to 1 by root of LC. This is one of the most important expression. Why? Because this is a one of the frequency. This is a particular frequency which makes XL minus XC equal to 0. That means XL is equal to XC. The inductive reactance and the capacitive reactance both are equal at a particular frequency. That frequency is called as omega, which is called as natural frequency. Otherwise, it is said to be resonant frequency. Why it is called as resonant frequency? We will discuss later. Now, let it be taken as natural frequency. Okay, here omega is the natural frequency. In this particular frequency, XL and XC are equal. XL minus XC equal to 0. Then Z minimum, the impedance become minimum and it will be equal to only resistance. The other two terms XL and XC are cancel out each other. So Z minimum equal to resistance. Here the impedance is very low. Z impedance is minimum. So the current will be maximum. So the maximum current will pass through in the circuit. The current will be peak. Maximum current, maximum AC current will pass through the circuit when we are applying the EMF at this particular frequency, that is natural frequency. When we are applying EMF at this particular natural frequency, then the impedance becomes minimum, current flows through the circuit becomes maximum. The applying frequency matches with the natural frequency, then the condition is called as resonance. Both frequencies are similar. Applying frequency, the frequency of EMF equal to E naught sin omega t. Here omega is the angular frequency. This applying frequency, which is equal to the natural frequency of the circuit, then resonance takes place. That phenomenon is called as resonance. During this resonance condition, XL minus XC equal to 0. The opposition given by the inductor and the capacitor cancel out each other. So the resistance is the only opposition. That means impedance becomes minimum and the current flows through the circuit will becomes maximum. That is the resonance condition. That is the speciality of resonance. That is one of the most important term we learned. What is resonance? We know. Okay. So please remember, resonance is nothing but the applied frequency and the natural frequency matches. When we are tuning the radio circuits, when we are tuning the radio circuit, when the applied frequency and the natural frequency will match, then impedance becomes minimum, the current passing through the circuit becomes maximum, then the noise level will be less. We can hear the sound with super clarity. Okay, that is the secret behind this. Okay, this is what when Z becomes minimum, when Z becomes maximum. That is the second case we are going to discuss now. When Z becomes maximum. This will happen in two cases. First, case number 1. In the case number 1, we can use this expression R square plus XL minus XC the whole square. If XL and XC are equal, they will cancel out each other. Okay. If XL is greater than XC, that means XL is greater than XC means L omega is greater than 1 by C omega. Okay, L omega is greater than L C omega. No. I will tell you in another way. If the applied frequency is greater than natural frequency, if the applied frequency is greater than natural frequency, what will happen? What will happen? This is what? XL is equal to L omega. This is what? XC is equal to 1 by C omega. Okay, both are equal in the resonance condition, then the impedance becomes minimum, current becomes maximum. But in this case, when we are applying, the frequency of EMF will be maximum than the natural frequency. What will happen? If the frequency increases, XL will also increases. The inductive reactance increases with increase in frequency because both are directly proportional. So XL increases. XL goes higher. When angular frequency of EMF, when the applied angular frequency of EMF increases, XC decreases. That means capacitive reactance decreases in this case. So it comes down. Okay, it comes down. Then what will be the impedance? Then Z is equal to root of R square plus XL minus XC. That means this is the variation. This is what? XL minus XC. So XL minus XC is there. Here XL minus XC has certain value. Because XL goes higher, XC comes down. So there will be a difference in values between XL and XC. That makes impedance becomes higher. Okay. The next thing is, when we are further increasing the angular frequency, applied angular frequency with respect to natural frequency. If we further increasing applied angular frequency with respect to natural frequency, what will happen? It goes higher, it comes down. So the difference is bigger here. XL minus XC is greater. Here XL minus XC is greater. That means what? When we are applying the applied frequency is greater than the natural frequency. Whenever we are going far away from the natural frequency, the value of applied frequency is far away from the natural frequency, then Z goes on increasing. The value of Z goes increasing. The value of Z is gradually increasing, or it goes on increasing when we are going far. When we are going far means when the applied frequency is going far from the natural frequency. How far it is increasing from the natural frequency, then the impedance value goes on increasing. Okay. Then next case, the second case is what? The second case is applied frequency is less than natural frequency. What will happen? When the applied frequency is less than natural frequency, this is what? XL, XC, both are equal, then the condition is resonance, then peak current will flow through the circuit, that we know. Here applied frequency is less than the natural frequency, that means XL is equal to L omega. If we are decreasing the applied frequency, the inductive reactance decreases, but capacitive reactance increases. That means XL comes down, XC goes up. So the difference is created here also. Whenever the difference is created between these two values, the impedance goes on increasing. The same thing happens here also, because this is directly proportional, this is inversely proportional. So the same thing happens here also. If we further decrease the angular frequency, it will further increase, XC will further increase. So there is a lot of difference between XL and XC. it makes Z becomes higher and higher. So as the applied frequency goes far away from the natural frequency, the Z goes on increasing. So there is no maximum limit of Z. There are two cases. In the two cases, omega A is greater than omega or omega A is less than omega, Z will increase depending upon we are increasing or decreasing the applied frequency. Okay, these are the two possible cases. Z goes on increasing. If the Z is increased, then what will happen? The current passing through the circuit will decrease. In both the cases, the current passing through the circuit will definitely decrease. Okay, so this is the thing we learnt. This is the thing we learnt, but it is very easy to learn this thing with the help of graphical representation. Let us wait. This is omega naught. Omega naught is the natural frequency. Let us take. This is in the x-axis omega, y-axis current is taken. Okay, I. This is what I naught. Wait. Okay. Take a graph. Draw a graph between omega and I. Omega is the angular frequency, applied angular frequency. I is the current passing through the circuit. Okay, when the current attains its maximum value, when the current is higher, when the peak current passing through the circuit, the answer is only one. What? When we are applying the EMF of its natural frequency, when we are applying the frequency of EMF is matches with the natural frequency of the circuit, then the current will becomes maximum, impedance becomes minimum. Okay, where it is. So this is what natural frequency. In this natural frequency, the current reaches its maximum value. That is what I naught. I naught is the peak value of the current here. This is what I. This is current. This is peak current. This is angular frequency. This is natural frequency. Okay, then we are decreasing. Then we are decreasing the applied frequency. The current will decrease. For this. For this. For example, this. Likewise, when we are increasing the angular frequency, the current will decrease because impedance increases. When we are further increase the angular frequency, the current will decrease because what? Because impedance increases. Connect the graph here. Yes. Okay, this is the point. So connect. This is the graph. What this graph shows? What this graph shows, when we are applying the frequency equal to natural frequency, the impedance is minimum, the current goes to its peak value. Otherwise, the current will be less. The current goes down. The current goes down whenever we are decreasing or increasing the frequency, applied frequency. That is the thing we learn from this diagram. Whenever the current is less, the power is also less, because the formula for power is equal to, we know very well about that. P is equal to I square R. P is equal to I naught square R here. Here the current is, in this point the current is I. So here P equal to I square R. Okay. In this place, this is the peak value of current. In the peak value of current, the impedance is minimum, which is equal to what? Which is equal to only the resistance. So we can write here I naught is equal to E naught by Z. Here Z is minimum at this condition. At this condition, Z is minimum. Z minimum is equal to nothing but resistance. So I naught is equal to E naught by that is resistance. Okay. Then what? Yes. Here inductive reactance and capacitive reactance can be changed with the help of angular frequency. Okay, good. If we are changing the value of resistance at a particular frequency, for example natural frequency, here the natural frequency, here the applied frequency and natural frequency matches resonance condition, so the current attains its peak value. In this condition, if we change the resistance of the circuit, what will happen? What will happen? That is the question. What will happen means the same thing is followed, but the peak value of current can be different. The peak value of current can be different. So we can change the peak value of current without changing the angular frequency, without changing the natural frequency, without changing the applied frequency. That is the correct word. We can change the peak value of current without changing the applied frequency by changing the resistance, by changing the value of resistance. You can able to change the value of resistance. If you can able to change the value of resistance without changing the applied frequency, when the applied frequency and the natural frequency are matching together in the resonance condition, then the peak value of current may vary. When the peak value of the current will definitely vary, not may vary, it will definitely vary. So we can able to increase or decrease. This is about our wish. Okay, we can able to increase or decrease the peak value. Okay, in these three cases, for example, this is resistance 1, this is resistance 2, third one is resistance 3. Okay, which is greater? Which resistance is greater here? R1, R2, R3. Three resistors are connected in the circuit at a particular frequency. Okay, it attains the maximum peak value. Which current? Okay, there are three peaks, three graphs we drawn. Okay, in this, which is greater? R1 is greater than R2, is greater than R3, or otherwise R3 is greater than R2, is greater than R1. There are two possibilities. We can easily find the current is maximum. So here the current is maximum according to Ohm's law. The current is maximum, so the resistance and current are inversely proportional. We know resistance and current, these two are inversely proportional. So when the current is maximum, the resistance is minimum. So accordingly here R1 has greater current and lesser peak value of greater resistance, the peak value of current is lesser. Here lesser resistance, here peak value is higher. Here very less resistance, so the peak value is much higher. So R1 is greater than R2 is greater than R3. This is the thing we learned from this graphical representation. Okay. Last one thing I want to tell you. At a particular value of the current, the power will be half. At a particular value of the current, at a particular value of the current, the power will be half. In which value? The power is half. I said power is half, so I put half I naught square R. Here power will be half. Okay, is equal to the particular value of current I said. So I want to find the current. That means this is power, which is equal to half of the maximum value of the power. So R get cancelled. We need I. So I square equal to I naught square. So I equal to I naught by root 2. I is equal to I naught by root 2. This is the particular value of current. In this particular value of current, the current will be half. For example, this is I. Okay, this is equal to I naught by. For example, if consider I is equal to I naught by root 2, then the power will be half. Power is half. Power will be half. Half I naught square R. Okay. At a particular value of current, the power will be half. What is the particular value of current? I is equal to I naught by root 2. This will be helpful in future. Okay. Okay. Now let us discuss the final. We are in the final step. That is what? From this graph, at a particular frequency, the natural frequency and the particular frequency both are matches. Then there is a resonance condition. In the resonance condition, current reaches its peak value. Okay, current reaches its peak value. That is Z is minimum, impedance is minimum. Z minimum is equal to resistance, because the opposition given by only is resistance. One thing. Okay. So when the applied frequency is increased or decreased than the natural frequency, the current will decrease. The power will also decrease. The current will decrease, so the power also will decrease. Okay. Last one thing, just wait. Here the current is maximum. Here the current is maximum. Here the current is less. Likewise, here the power is maximum. Here the power becomes half, because I equal to I naught by root 2. So between these two values, what? For example, these two values, 1, 2, 3, 4 and 5. So at the resonant frequency, the current will be maximum, power will be maximum. When the frequency decreases, the current decreases, power decreases. When the frequency gradually decreases, all these cases, the current will decrease, so the power will also decrease. At this frequency, the current becomes I equal to I naught by root 2, so the power becomes half of its value, half of its peak value. So the power is half here. Okay. So at this particular frequency, the current will be maximum. So we get in the radio tuning circuits, we matches the frequency at this resonant frequency. We will get a clear sound. Radio tuning circuit, we will get the clear sound. That means noise reduced sound we can get at a particular frequency, because the current passing through the circuit will be maximum here. This will be the technique used in the radio tuning circuits. Okay. When we are applying several frequencies, for example, from this frequency to this frequency, large number of frequencies. For example, this frequency to this frequency, large number of frequencies, and EMF E equal to E naught sin omega t is applied in the AC circuit, in a radio tuning circuit. We can able to hear from this to this. We can able to hear the sound from this to this. All are audible. We can able to hear the sound. But this sound is much clear. Because the current is peak. This sound is less. This is very less. This is very, very less. So the sound goes on decreasing when we are decreasing the frequency, applied frequency from the natural frequency. Not only decreasing or increasing. Okay, so but we can clearly audible only at the particular frequency. Okay, we will learn what are the things in this class. The variation of Z. When the Z is minimum, when the Z is increasing, there are two cases. Omega is greater than A, omega is greater than omega is less than omega. What is resonance? What is resonant frequency or natural frequency? How the graph connects? What is the important thing we learn from graph? Can we vary the resistance without changing the resonance condition? Yes. How? These things are we discussed in this class. We are going to discuss in the next class the tuning circuits. That will be more interesting and much useful for you. Till then, thank you, my dear friends. Thank you.